Ladies and gentlemen, welcome to the joint programs of International Conference on Radioscience, Equatorial Atmospheric Science and Environment, and the 6th Asia Research Node Symposium on Humanosphere Science. In this meeting, I would like to give a presentation with the title Langley Plot and LAMBERT-BEER Law in Retrieving Solar Intensity at the Top of Atmosphere for Monitoring Aerosol Optical Thickness. Here is the outline of my presentation today. I would like to start from introduction, then continue to the methods, result and discussion, and I will finish with the conclusion. Now, I start from the introduction. In this part, I would like to explain the general and specific motivation in this study. As we know, aerosol is a tiny particle floating in atmosphere. The aerosol play an important role at the Earth of radiation budget and the air quality. From the previous study, here I would like to show the study in Italy and in Japan. This is my previous study. Both of these studies show that the aerosol accumulated in the lower troposphere. It's about 2 kilometers from the ground. And also we know there are some aerosol optical properties. For example, aerosol optical thickness. Aerosol optical thickness is a transparency in atmosphere. And sometimes aerosol optical thickness will represent as an integration of extinction coefficient. And the second one is single scattering albedo. The single scattering albedo means the ratio of scattering efficiency to the total extinction efficiency. Asymmetry parameters mean the angular distribution of the scattered radiation. The aerosol extinction coefficient means attenuation of light due to aerosol. Right now, I just focus to the aerosol optical thickness. Furthermore, the specific motivation in this study is the role of aerosol in remote sensing satellite. As we know, in the remote sensing satellite, especially for the optical remote sensing, the interaction between radiation from the sun with the object in the ground, there are 6 elements of scattering. To study about the scattering, we need one of important parameter named apparent reflectance. To know the apparent reflectance, we need a look-up table between aerosol optical thickness and apparent reflectance. If we want to know apparent reflectance, we need information about aerosol optical thickness. That's why the aerosol optical thickness is very important to study about scattering in remote sensing satellite process. The next, I want to show the methods to obtain aerosol optical thickness using sun photometer data by employing Langley plot and LAMBERT-BEER law. In this scheme, we can see how the sun photometer to measure the solar intensity. The procedure of sun photometer in recording the solar intensity start from the sunlight above the top of atmosphere in coming to the low level of atmosphere. Then the sunlight scattered by the aerosol particle. And the final process, the unscattered sunlight recorded by sun photometer. From the procedure, we can obtain the solar intensity in the temporal change plotted automatically by the sun photometer system. We can see in panel B. And the solar zenith angle and solar azimuth angle is plotted manually based on data which recorded at the same time of the solar intensity. This is a formula to calculate total aerosol optical thickness with a correction factor of gas and molecule. From the solar intensity data at the most clear sky condition, we can do a Langley plot to obtain the solar intensity at the top of atmosphere. In this formula, ln I lambda mean a logarithmic of solar radiation derived from this plot procedure. This is an example of the logarithmic of solar intensity as a result of Langley plot process. The complete procedure in calculating aerosol optical thickness is explained from this formula. Ln I lambda derived from a Langley plot. Ln IC lambda is the solar intensity from the sun photometer data in the measurement target, together with air mass data. In this calculation, we employ a correction factor of ozone gas using satellite GOM and molecule correction based on ambient pressure derived from the local station. Next, I will show the main result based on the methods we employ in this study. The first result is a logarithm of the solar intensity obtained from the Langley plot based on their wavelengths. We can see here for 368 nanometer, the logarithmic of solar intensity is approximately minus 14.8. And the next, for 500 nanometers, we can see the logarithmic of solar intensity around minus 13.4. And then for the 645 nanometer, we can see the logarithmic of solar intensity about minus 13.2, which means the shorter the wavelength, the lower the logarithm of solar intensity. The final result of this study is the temporal change of aerosol optical thickness. Panel A shows the temporal change of aerosol optical thickness based on sun photometer measurement. The result has been compared with an independent measurement using sky radiometer. We can see in panel B. From the result, we can claim that the method we used in this study is applicable in processing the sun photometer data with uncertainty about 50%, which means the error of this method is about 5% compared with the sky radiometer data as an independent measurement. Ladies and gentlemen, brother and sister, finally, from this study, we can conclude that the Langley plot and Lambert-BEER law has been employed in retrieving of the logarithm of the solar radiation at the top of atmosphere in the most clear sky condition close to the measurement target. The temporal change of aerosol optical thickness is derived from sun photometer data processing. The correction factor employed in computing of aerosol optical thickness are ozone gas contribution derived from GOM-2 satellite and carbon dioxide molecule derived from local station. From the overall procedure, we can estimate the aerosol optical thickness values with uncertainties of approximately 5%. That's all for my presentation. I would like to say thank you very much for your attention.